Hi, and welcome to this session on toward net energy, data centers and supermarkets. I have a very exciting panel here with me today, who's going to talk about why it's important to reach net zero energy data centers and supermarkets and how we're actually going to do it. First off, we will have Kevin Lane, who is the policy analyst for the IEA, the International Energy Agency, who will present their view on data centers and supermarkets and why it's important from also a policy perspective. Then secondly, we'll have Drew Turner presenting how we reach a net energy zero data centers from a Danfoss perspective, in particular from an oil-free perspective. And then lastly, we will have Hans Ole Matthiesen presenting how we reach the same on a supermarket level. So with that, Kevin, I'll just pass it over to you.
Thank you very much, Jonas. And thank you very much for the invitation as well. It's great to be part of this really interesting series presentation with some great content to follow. Also, I'd like to take the opportunity to welcome our attendees as well, and just to say wish that they're well in this time of health and economic crisis. But what I'm going to talk to you today is more about our climate imperative to try and reduce carbon emissions by using energy more wisely, and specifically with respect to data centers and supermarkets. If we look at energy-related CO2 emissions around the world at the moment, they're probably around 33 gigatons. This year might be a little bit low because of the COVID pandemic, but we're still pretty much on an upward trend. With policies at the moment, we might level that off and still leave it about 33 gigatons. However, what we really need to do is decarbonize quite substantially by 2050, and maybe a bit beyond that, get to almost net zero emissions. And to do that, we're going to have to use a range of measures, whether that's increased efficiency, renewables, and maybe some other technologies as well. And that's to realize our sustainable development scenario, which we have at the IEA, and that is to try and put the world on a pathway towards 1.5 degree raise in temperature by the end of the century, but also to reach our sustainable development goals, which is to help society in the developing economies to have clean cooking and better access to electricity. So some of the end-use technologies or measures that will be needed are listed down there on the right, whether that's more efficient buildings, maybe more renewables, and fuel switching included in there. So at the IEA, we also track a lot of these technologies. We track 46 separate ones in our Tracking Clean Energy Progress, and one of those is data centers and networks. And at the moment, they're one of the few technologies or sectors that are really on target to meet this sustainable development scenario. So data centers are in a good place in that respect. They also overlap with some of the other technologies as well, perhaps demand response, smart grids, as we'll see during the next hour or so. Okay, if we look at data centers and energy use, at the moment we think that they're using maybe 200 terawatt hours as our best estimate, and surprisingly that hasn't increased dramatically over the last 10 years. And most of that is because of the switch to very large scale data centers, which are a lot more energy efficiency. So the efficiency of these products has doubled maybe every 2 years. It's quite incredible, the efficiency improvements that these have made. So it means that over the last 10 years, we've almost seen a tenfold increase in the use of data centers, internet traffic, and yet we've managed to stabilize electricity consumption around the world, which is about maybe 1%, could be a bit higher than that, up to 2%, say, of global electricity demand going into data centers. So perhaps there's not a problem globally in terms of the energy consumption. However, if you drill down to certain countries, so for example, here we see Ireland, and their energy consumption over the next 10 years for data centers is going to be about 30% larger just because of data centers. So for Ireland, there's some reasons why data centers are being put there, whether it's better fiscal conditions to be closer to some of the markets. But Ireland's one of the countries where you will see a big rise. Denmark will also see maybe a 15% increase in electricity due to data centers. So if we look at data centers, there's there actually can be very large now. These hyperscale data centers, which are run by a company like Google, Facebook, they are very large, requiring maybe 100, 200 megawatts of power to run them, and they're consuming huge amounts of electricity. So there's been quite a move to improve the efficiency, and there are some standard ways of improving them. That's mainly around improving the cooling of them, and we'll hear a good presentation later on that. However, there's other things that can be done. One of them is that these data centers, they actually very good at having adjustable load, so they can fit in very well with renewable energy, especially variable renewable energy. So we see that a lot of these very large data centers are purchasing a lot of renewable electricity, so purchasing power agreements. So you can see these big ICT companies like Facebook, Amazon, Google, they're buying significant amount of renewable energy, and they can manage that on their sites. They can also be installing a lot of renewable energy as well as doing a little bit of storage to try and manage that grid. So they have got some opportunities to do that. However, another really interesting part of this is there's still quite a lot of, I guess, waste heat coming from these data centers, and I think it's interesting to see how can we use that energy locally, maybe combine it with other sectors as well to make best use of this energy that we're putting into these data centers. On a similar track, I just want to show you one side in supermarkets. If we look at supermarkets, they're probably consuming about 2% of all electricity in Europe, maybe a bit higher, could even be 3-4% across all industrialized countries. Unlike data centers, they're not a huge amount in terms of megawatts consumption. However, there are just lots and lots of them. And typically for an efficient supermarket, it might be using, say, 400 kilowatt hours per meter squared. And that would be the case in, say, Denmark. It might be higher in a country where there's more heating or cooling, or maybe where the opening hours are a lot longer, so say USA or Canada. When we look at the energy consumption, maybe half of that could be due to refrigeration equipment, and then there's all other ancillary equipment and heating, cooling around the building as well that could be needed. And we'll see more detail on that later. In terms of the broad opportunities for improving the efficiency, well, there's all the components which are relatively straightforward to do from a policy perspective. We have good regulations in terms of eco-design, better information, perhaps incentives to try encourage more efficient uptake. But I think some of the interesting parts is how we try to optimize the system as a whole. How do you better manage heating and cooling and map that out better, but also even integrating the demand with the grid as well. I think that's for both sets of applications. So in addition to that, then I guess it's how we manage some of this waste heat. Can we again use it nearby? Are there any other sectors we could use it for? So I'd like to conclude basically by saying, yeah, we have got a very large climate imperative to substantially reduce our carbon emissions, and making our supermarkets and data centers more efficient and smarter is definitely one of the key things that we need to do. For data centers, I think they're pretty much on track, and we have got a good idea of how to improve the efficiency, how to match their demand with renewable electricity, maybe some storage, and I think we're starting to get some ideas of how to use waste heat. Similarly for supermarkets, I think good opportunities exist for both of those. I think the two presentations that follow will give a lot more detail and some rather exciting ways of managing these. So with this, I'd like to hand back to you, Jonas.
Thank you very much, Kevin. I thought it was very interesting to hear about the opportunities that you see, even though that you mentioned 2 to 4% of total energy for supermarkets and 1 and maybe a bit more of energy in relation to data centers. It sounds like there's still opportunities, and maybe even opportunities going beyond the energy efficiency side, and how to make these two energy consumers an active part in local communities. I also noticed that there are some specific opportunities. You mentioned Ireland and Denmark, and it really depends on local conditions. And I think you also mentioned this about the large or the hyper data centers, and I know that that's something that our next speaker, Drew Turner, he will touch upon. So with that, I'll leave it to Drew, and just to say, Drew is the global marketing manager for oil-free solutions at Danfoss, and he has more than 20 years of experience within this field. So Drew, I think yes, perfectly. So I'll leave it to you, Drew.
Okay, thank you, Jonas. Yeah, thanks for the opportunity as well. So, and thank you, Kevin, for really setting up the presentation as well. So, as Jonas mentioned, I'm from Danfoss Oil-Free Solutions, and I'm going to be talking about getting to net zero data centers specifically with Danfoss Oil-Free Systems and the turbo core compressor technology. What we see in terms of design trends for data centers is a combination of moving towards free cooling or reduce or increasing the cooling temperature and or reducing the heat rejection temperature, and then also getting closer to the CPU. So it's a combination of related factors that we see. How they get lower in the heat rejection temperature is a combination of factors also, and it depends on the solution that's utilized. But what we see is that, especially when the data center, and I'll get to this in terms of the segmentation of the market of data centers, but we see that the market, especially with the larger enterprise, as Kevin talked about, they have the geographic location flexibility to put these data centers in areas where they can reduce the heat rejection temperature. But I'll talk a little bit more about that later. And then the cooling temperature, what we see is that as you have come to the realization that, or as the market and the application have come to the realization that you're not cooling people here, you're cooling the equipment, that in turn means that you can go higher temperature and also get closer to that heat generation equipment. And so we see that significantly impacting the design and the operating temperatures. And then decreasing, as I mentioned, decreasing the heat rejection temperature based on a combination of solutions as well. The whole goal with cooling, and so for data centers, the main goal is to generate cooling, first of all, to cool to reject the heat from the IT equipment itself. And how they measure the efficiency of the data center ties to that. How they measure the efficiency of the data centers is what's called PUE, or power usage efficiency, and that in turn is driven by the total facility power consumption annually divided by the IT equipment power consumption annually. And what you see with data centers is that they measure this in terms of both the design as well as the real-time operation, also resulting in, of course, the annual as shown here. And as they measure that, they've come to the realization that, okay, anything that's not being used to directly run or power the IT equipment is waste. And so the goal is to completely get rid of that as much as possible, or to lower it down. And the result is, as shown here, you decrease the PUE levels. And so specifically what's shown here is a decrease from around 1.4 to 1.3 to 1.25. But the critical side note is the air-cooled cooling resource. As you see, with the power usage efficiency decreases and the progression of that, you see a corresponding decrease in the usage of energy specifically for the cooling equipment, which in turn, of course, means higher efficiency. And the trends that I talked about earlier, and I'll detail more later. But the main factor here, and tying this back to what I was mentioning on the first slide, is the progression of technology that's utilized for cooling of IT equipment or data centers. So what we see is when data centers first came into being, roughly 25 to 30 years ago, they were designing them basically the way that you were designing a comfort cooling system. And so with those comfort cooling system, you have an operating temperature that's driven by both the sensible load of mechanical equipment or people loads as well, but it's especially a sensible load, but then also the latent load. And latent load is driven also by people as well as the ventilation error, but especially the ventilation error. If you only have sensible load, which is what an IT facility is or what a data center is, then you can change that operation. And so that's driven the progression that we've seen. So when room-based cooling was first created for data centers, it was mainly DX. That has evolved to, of course, to chilled water cooling, which is basically at maturity. And then row-based cooling, getting the cooling closer to the IT equipment and specifically the CPU that generates, or central processing unit that generates the heat. Then as that progression moves on to rack-based cooling, and then the ultimate solution here. But before that, that's getting closer to the equipment and higher temperature based on that sensible load. This one is based on free and adiabatic cooling is on the heat rejection side. So lowering down the heat rejection temperature to also increase the efficiency. And what we see is that on the air side, that this is becoming much more prevalent. Also on the mechanical or refrigeration side as well, with indirect adiabatic cooling or evaporative cooling. The ultimate direction that we see is that as you get closer and as you get higher temperature, as you get closer to the CPU and as you get higher temperature, the ultimate goal is to potentially do direct on CPU cooling, either through liquid immersion or a cold plate on the CPU or something like that, but potentially without, based on that higher operating temperature, without mechanical cooling on the refrigeration side. So that basically summarizes what I've been talking about, getting to more efficient cooling and therefore better PUE. That's the main focus of data centers so far. And on that, specifically with the R technology. So this is where I transition to talking about the Danfoss technology and specifically the turbocore compressors for it, and how it fits with both trends. So as you increase the cooling temperature and as you decrease the heat rejection temperature, the result is lower lift or lower differential temperature. If you have equipment that can operate at those minimal differential temperatures, then you have more efficient equipment. The thing about oil-free systems, whether or not they're Danfoss-based systems or systems based on other people's technology, but if they're oil-free systems, they can, in general, operate at those lower lift or lower differential temperatures and lower pressure ratio, resulting pressure ratios. And this is highlighting that. What you see on the right-hand side here is the operating map with the suction temperature or the evaporator coming into the compressor on the low side, and then the discharge temperature or the condensing side on the high side on the vertical axis. And the combination of those drives the pressure ratio, which is the dotted line here. And what you see is that with screw compressors or other positive displacement compressors where you have oil and you have oil moving through the system and you have to return that oil back to the compressor, it is that differential pressure that drives that return of the oil back to the compressor. If you have no oil, with an oil-free system with turbocore technology, then you have no oil to return, and therefore you can theoretically turn down further in terms of the pressure ratio, resulting in more efficient operation. That's why you see, whether it's again with our technology or those of others, that oil-free technology has become so prevalent in data centers today because they are lowering down that heat rejection temperature and they are increasing that cooling temperature, and therefore operating at the lower differential, and therefore this technology is a perfect fit to optimize the efficiency for it. And this is just showing examples of our compressor technology for those applications. The main point here, and this is only true for Danfoss today, is that we have compressors that are optimized to those specific conditions that they will operate at. So we have a broad portfolio, whether it's for standard or medium lift or high lift applications where you're in turn going to higher differential temperatures and pressure ratios, and our optimization to the standard lift applications, including water cooled chillers and air evaporative cooled chillers or adiabatic cooled chillers, is this portfolio here optimized for these lower lift designs. But what we also see is the medium lift utilized depending on the heat rejection temperature. So if they can't drive down the heat rejection temperature, and I'll come back to that in a minute, then it's going to be more of a fit with the medium lift operating temperature compressors. With the data centers, and I talked about this a little bit earlier, we see really two distinct directions. And this is really driven by the segmentation of the data center market itself. What we see is that with the co-location facilities, and this is an oversimplification of the market, but basically what we said is there's two main business models with data centers, and they really fit with the design trend for them as well, both the cooling side as well as the data center side itself. And with the first category, we categorize it as co-location. And the co-location are the ones that are managing data for others. And that, as opposed to that, you have more the enterprise and cloud data centers, which are managing in general, managing their own data. There's a lot of crossover here, and it misses, of course, the other big trend that we see around edge data centers, which fit with both. But it's a good segmentation relative to what we're trying to get across here today. And so with the co-location data centers, they're much more focused on increasing the cooling temperature. And the reason for that is because they have to be in the locations of their customers. And that includes Phoenix, Arizona, or Rome, or Guangzhou, or Singapore, where you're going to have a limited capability to drive down the condensing temperature. And so they're focused much more on increasing the cooling temperature to, in turn, drive better efficiency and lower differential temperatures. As opposed to that is the enterprise. And Kevin touched on this earlier, but the enterprise are getting bigger and bigger. And this is true somewhat with the co-location as well, that they're getting bigger, but we see this much more the case with the enterprise data centers. The other thing that's happening, though, as they get bigger to these mega data centers, they're also trying to locate them in the northern geographic climates where they can drive down that condensing temperature and get the efficiency that way. They're also trying to increase the cooling temperature, much the same as co-location, but it's more critical and more possible to drive down that condensing temperature. And so that's why you see these data centers being built in Denmark and in Sweden, where they can drive down that condensing temperature. So in terms of bringing it all together, data centers are trying to push up the cooling temperature, drive down the condensing temperature, and there's a difference in what we see with the enterprise data centers versus the co-location data centers in their main focus on doing that. What's really been missing from this discussion, and what's missing entirely from a PUE measurement, is the rest of the story of how you get to a net zero data center. And that's where we come in. And that's where we're advocating a change to how they design the systems. And you already see this happening also in some of these new data centers that are being created in Denmark and Sweden, for example. And what they're doing, or what we see as the biggest opportunity, is to capture the heat rejection. And Kevin touched on this briefly a little bit earlier. But when you're capturing that heat rejection, it's much better to tie it to a district energy system so that you can fully utilize that heat that becomes available, because that's higher than the capacity than the cooling system itself, and I'll come back on that. But if you integrate into a district energy system, it also provides a much better solution for the overall heating and cooling market. With the natural progression of electrification of heating, what we see is that the realization is coming about also that for both cooling and for heating, all you're doing is moving heat. And so when you realize that symbiosis aspect, that you're just moving heat from the cooling side to the heating side, then you integrate in those systems. And when you integrate in those systems, then you drive both the cooling as well as the heat recovery based on the full capacity of what's possible with that. And when you do that, it's best to tie into a district energy system on the high side or on the heating side, so they can make full use of that. That district heating system also enables multiple options for thermal storage, which also become more important, and I'll talk about that in a minute. And on-premise renewable production. So renewable production becomes much more flexible in terms of where you can integrate it into the system. And also with the oil-free solutions, it also enables the ability to utilize the lowest GWP refrigerants available on the market. But with the district energy grid, a couple things I want to point out here, and this is just showing an example of that. With the red line, of course, showing the district heating supply line or the high temperature, and then the yellow line or orangish yellow showing the return line or the after the heat has been utilized at the facility. But what we see is that with the integration of more heat pumps into the district energy grid, that there's much more of a focus on this symbiosis aspect applications, where as opposed to a centralized heat pump system, you have the opportunity to generate the heat based on heat recovery at a higher temperature, which in turn means a more efficient heat pump. And also, another thing that I want to put on here is, because these renewables are only available when they want to be, the wind's only blowing when it wants and the sun's only shining when it wants, it becomes very critical on the demand side to reconnect that supply and demand. And how you do that is by a combination of storage, which I touched on a little bit earlier, but also creating demand response flexibility in terms of critical facilities and operating their backup power systems. And what you'll notice is that a majority of these cooling systems, whether it's industrial process heat recovery, food retail heat recovery, or hospital heat recovery, or as we're talking about today, data centers, most of these are critical facilities, meaning that they have on-site backup power generation anyway. Utilities are already working with these guys to be able to incorporate them in their demand response programs such that they can run those backup power systems when the wind's not blowing or the sun's not shining. Now, if you integrate it in with a district heating grid, you also supply the heating to the city based on that same backup. So the summary or the theme here is, instead of what we see, and this is showing the example from back on the co-location data center, instead of moving to higher temperature or just higher temperature cooling and keeping the heat rejection at the same temperature or lowering it down in the case of the enterprise, you take that enterprise data center and you increase the heating temperature up to where this profile or the overall differential temperature is roughly the same as the first generation data centers, and generating cooling with an air-cooled chiller and cooling at the comfort cooling temperatures. But now, instead of just generating cooling, what you're doing is generating the heating as well and capturing all that heat and supplying it to the district heating system, and also generating all the revenue associated with this. So again, as I was talking about with data centers, they're focused on PUE to improve the efficiency of their systems, to improve the profitability of their business. And they're very sensitive about sharing that PUE information because it also implies what they should be selling their data services at. And if you add in an additional revenue source to that, it significantly improves their business model as well. So instead of just focusing on PUE and optimizing that and their revenue source strictly based on those data services, you can add to that the heat recovery and the associated supply to the district heating system, selling it to the district heating system. Or as an alternative business model, and of course I know data centers are sensitive to this, to letting anybody in, but if the district energy utility is allowed to, they can come in and operate that system to deliver cooling to the data center and then recover the heat to the district heating system, that being the primary business. And for that higher lift application, of course, we have a portfolio of compressors optimized to those as well. And that's the other thing that we want to highlight is, with these optimizations, it's not only the low lift and it's not only the medium lift that I talked about earlier, it's also the high lift. And what we see for these heat recovery applications and for a specific industrial cooling example that we just worked on, some combination of these compressors is the optimal solution for any one of those applications. So for that industrial process, which is going to be very similar to a data center at a little lower cooling temperature, the optimal solution was medium pressure optimized compressor designs for the low stage of a series counterflow arrangement of those chillers and heat pumps. And then the high lift compressors designed for the high stage, optimized for that and the operation or the generation of heat on the high stage. The other thing, or the final thing that I want to highlight is, I've talked a lot about compressors. We have a broad portfolio and an expanding portfolio of compressors optimized to these applications, whether it's cooling only or cooling and heat recovery. The other thing that we like to highlight is that we design all of the components in the Danfoss portfolio specific to these applications. So whether it's our liquid level sensors or solenoid valves, check valves, heat exchangers, et cetera, they're designed to operate the most reliably and efficiently for the applications that they're targeting. That means that we test all of those components in the specific refrigerant environment, an oil-free environment, and the applications that they're going to end up being utilized in. That's as opposed to competition, which generally tests all those components in dry air, which does not reflect and guarantee a reliable and efficient operation in an oil-free application and with the refrigerants we utilize. And with that, I'll take it back to Jonas.
Thank you very much, Drew. I think it's very interesting to hear the latest trends that you're seeing in the market for data center, moving closer to the CPU, and thereby increasing the efficiency due to the temperature difference in the CPU that you're seeing. And it's also quite interesting to hear, that the oil-free solutions actually are quite good fit for data centers. And it's very important to optimize them specifically for both the local needs, as we heard a bit that Kevin mentioned, but also for the so meaning the city or wherever it's placed, but also for the data center and the size and that specific data center. I think it's also quite interesting to hear about how you can optimize, you could say, the general effectiveness of the full system, so integrate it into the district heating system, and thereby creating new business models for data center owners. And on that note, I would like to pass it on to Hans Ole Mathisen, who will then talk more about these new business models and how we see it from a supermarket perspective, but also talking about how we actually today going to net zero energy for the supermarkets. So Hans Ole, over to you. Hans Ole, I think you have to turn your mic on.
There we go. Thank you, Jonas. Yes, so supermarkets, of course, are also extremely important, as you mentioned, and as Kevin pointed out, they are accounting for between 2 and 4% of global electricity consumption. So what can we do about supermarkets, and is it possible to get to net zero on supermarkets? We of course have been looking into these questions, and we found that it should be possible, but let's look at this example here. So we found some steps to get to net zero. And when we talk about net zero, we talk about net zero billable energy consumption, and that's both the thermal and the electrical side that we combine there. And the steps that we use first, basically, you need to reduce consumption, then reuse whatever you can by recovering the heat from the refrigeration system. We need to create, so to generate some energy on the premises, so through renewable generation. We can then also flex. So that means that we can use the energy in the most flexible way with demand side management as well. And then finally, to make the equation go to zero, then we need to export excess heat. So for this, to make the case, we're looking at a discounter. This discounter is located in Northern Europe. It's a 1,200 square meter store. And the energy, the average power of the store, the average consumption is shown on the right here. Over the year, of course, it varies from winter to summer and day and night, but on the average, it's pulling about 38 kilowatts in the store. So a large part of that going to the refrigeration, a greater part even going to the heating, and then lighting and miscellaneous loads. Miscellaneous loads could be everything from bake-off, cash registers, and trash compactors, for example. So the first thing that we need to do, or let's say what we call the fruit on the ground, is basically to reduce the energy consumption. And there are many ways to do that. The chart on the left here is basically a study done by the German Association of Mechanical Engineers. And what they've done here, they plotted hundreds of stores, the energy consumption of hundreds of stores against each other. And they've also plotted them based on the year that they were built. And what we can see here is that the average of all the stores is the top red line. And the baseline, or the average of stores built in 2017, is the middle dotted line. And what we've done in this example is to draw from one of our test sites, where we plotted the energy consumption of that store using our new CO2 adaptive liquid management system. And basically what we do here is similar to what Drew was mentioning. We're trying to raise the suction temperature and lower the condensing or gas cooling temperature of the system, and thereby using less energy. And what we found there was that we could actually reduce the consumption by 25% on the baseline of 2017, 50% reduction on the market average on the refrigeration side. So quite a reduction, actually. But it's not just about refrigeration. We also need to look at other sources of energy and where we can save. And certainly lighting is an area. Many retailers have already switched to LED lighting. That's absolutely necessary. And LED lighting is not just LED lighting. There are also different types of lighting. But going to high efficiency lighting, you can reduce the consumption by 40% over fluorescent. In terms of heating, of course, it's important to insulate the store well. But what is also interesting is that if we can reuse the energy from the refrigeration system, so reuse the condensing side of the refrigeration system, then we can, the best way to do that is if you have a low temperature heating system. So floor heating, or even a ventilation fan coil, where you basically make sure that you have a low return temperature on the hot water going back to the recovery system. And this is really a precondition to have efficient heat recovery in a store. The last bit here is about the auxiliary equipment. And of course, it's important to have an energy management system in the store. And here, monitoring the system, for example, with the Danfoss Alcent services, that you can basically, turn off the lights, turn off those loads if they're still running. It could be bake-off equipment where you have ovens that are not being turned off by the people in the store. Here we have the ability to go in and do something, and based on our experience, there is the opportunity here to save about 30% additionally on the other loads in the store. So just by reducing energy, we're shaving off the first 8 kilowatts from these 38 kilowatts. And by the way, Kevin, he mentioned something interesting, and that was an efficient store. It uses about 400 kilowatt hours per square meter per year. And that's pretty much where we at on the baseline store that we're talking about here. So it's very, very close. So the next point here is to basically reuse or to recover the heat from the refrigeration system. And we can do that. We can cover the heating demand. We can even do more without even raising the discharge pressure or changing any settings on the refrigeration system per se. We should be able to cover about 30 to 50% of the heating demand. Of course, this depends on where you are in the world. The more northern latitudes, you will have a higher heating demand, and southern latitudes, lower heating demand. So there is a range, of course. But our experience shows that basically wherever we are, if we can tweak the system a little bit, then we can also cover the full demand. And for example, in this case, we could raise the discharge pressure by about 10 bar, and by doing so, increase the useful energy by 50%. And this is roughly 15%, 20% increase in the rack energy consumption. But this is very low compared to the amount of heat that we get out. So by increasing the energy consumption of the compressors by 1.2 kilowatt, we're getting about 30 kilowatt extra heat out, useful energy, so at a higher temperature level, basically. And by regulating the discharge pressure, we can thereby meet the heating demand. And to do that, we've also created a standard unit. So something that's simple for the retailers to install, something that is basically recovering the heat when it's available, and buffering it in these stratified tanks, buffering tanks. So it's actually an energy storage system that we're installing here, and a heat central. This actually won the Solar Impulse Efficient Solution in 2018, and it's able to provide hot water for the store. It has also the pump shunt. It's able to integrate to district heating systems. It's able to provide heating to neighboring buildings, and it's also integrating to the refrigeration system. So basically, this is a standard product that retailers can install both in new stores or in retrofit stores. And as you can see here, we're saving 15 kilowatts of heating here. So now we've really managed to reduce the consumption of this store. And just to illustrate this, we have a lot of cases here in Northern Europe where we have installations that are running well. I asked a colleague of mine, Preben Bertelsen, to go and to visit one of these sites just to show you what it looks like. He was out there yesterday morning. This is a store, Menu supermarket in northern Denmark, and here he is.
I'm standing in the north of Denmark, and I'm standing in front of a pretty new supermarket. It's 2 years old. It's from the chain Menu, and it's placed here in the north of Denmark. It's cold area, close to the coast. I'll go inside this shop and see if I can find Christian Best. I know from research that this shop is something like 1,600 square meters. That it is equipped with the refrigeration system. It's capable of moving 96 kilowatts on the MT and 25 kilowatts on the LT. And that's actually all I know. So let's go and have a look. Now I'm inside the shop, and I'll just show you how it looks like. It's a pretty nice shop. It looks like a standard or nicer Danish supermarket with the delicatessen department. I'm standing here together with Christian West, the owner of the shop, and I'm gonna ask him how's the business been and what is his experience with this installation with HI.
We got the unit 2 years ago almost, and it's been going really good. We have been making all the heat for the store for 1,600 square meters, all for ourselves, and haven't bought anything. Whilst we sold in the summertime, we sold to the local heating company, so we get a little payback from them. We use it for hot water, air condition, and floor heat in our back rooms. So it's been really, really good for us.
Okay, that sounds good. Thank you very much, Christian.
Yeah, you're welcome.
Has been running well and without any problems for this period, and he hasn't bought any heat from the district heating system at all during these 2 years. So he's a happy owner of this system.
Yeah. So this was an interesting story, just from standard supermarket, basically. And this chain menu has decided basically to install these units in all of their new stores, and we also have retailers that that are installing them in all of their sites, so in their retrofit stores as well. This is no issue. And interesting to see also that that now they're not only selling food, but they're also selling heat from the store. So really becoming an energy prosumer in this case. The next item here is, of course, to generate or to create electricity, and this, of course, can be done in different ways. What we see is that the photovoltaics is probably the best way to go, as on supermarkets you have a very large surface area that can be used. So placing photovoltaic panels on the roof is a good idea. In the store that we showed here, the total surface area was 1,200 square meters on the roof of the store, and in this case we're installing a system that is able to cover the load and not more than the peak load of the store. So in this case, it's an array that's about half of the roof area, 600 square meters, and on the average over the year, it will produce 6 kilowatt. That will be then the average reduction that we can get. The peak production, however, would be around 100 kilowatt. So in order to manage that, of course, we need to combine that with a battery system, so that at midday on the sunny midday summer day, that we can actually store that energy and use it. And not to run out of space either on the battery. So this is what we have also done. I'll introduce another case where we have done this, where we've installed our inverter technology and also lithium-ion battery system, photovoltaic array. There's also electrical vehicle chargers in this store. And we're also using a refrigeration system, a CO2 refrigeration system with heat recovery. This project and the work that we do here, it's also in part together with SMA, and also on the let's say the service side, we also have a cooperation with Microsoft. For this example, I want to go to Germany, northern Germany, and Oldenburg, where we have installed a system in an Active and Irma store. And so what have we done in Oldenburg? So basically, in this store, we installed also this 99 kilowatt peak system on the rooftop, and it produced, I think last year, 112 megawatt hours of electricity. And as I mentioned, it's best that it can consume most of that itself, and it consumed 98% of the electricity itself. And what it didn't consume itself, it was then sold back to the grid. So this accounted for a savings of 14,000 euro in that year. And then on top of that, what we can do is we can begin to play around with the battery, and we do that in this store where we basically shave peak demand at midday. So when you have the warmest hours of the day, we can reduce the energy consumption of the store. And of course, the energy consumption at the peak hours is relatively more expensive. So by shaving the peak hours, by flexing, if you like, we've also provided savings of an additional 3,000 euros in this store. And what else can we do? So going forward, basically, we're starting to look at also incorporating the cooling system. we're using our Alsense system to so monitoring and services to basically monitor the store. We monitor everything, all the electrical consumption of the store, heat production, photovoltaic production, and so on. And by incorporating the refrigeration system in, we could also provide load shifting. And this will require some artificial intelligence, AI, where we can look at different patterns and then begin to reduce the temperature, for example, of the frozen foods at certain times of the day, and then let it float up. We can also shift defrosts and other things to really actively manage the energy consumption of the store. So these are some of the things that we'll be doing going forward, and that we're already beginning to experiment with. Finally, we can transform the store into a power station. So the last bit to get down to zero net, we basically use the refrigeration system to its full potential. And in areas where you have district heating, or where you're placing the store in an apartment building or offices, shopping centers, you can actually use the heat from the refrigeration system. In fact, the refrigeration system, it's a 60 kilowatt system, and on average, it's only using maybe 20 or 30% of that capacity. And that's of course because it's dimensioned for the warmest day of the year. If you can imagine that you could put an extra, let's say, air source heat load on external to the building, then you can actually run the refrigeration system as a heat pump. So you're not sacrificing anything inside the store. The food quality is taken care of, but you're able to actually actively provide heat to the grid when it's needed. If only 35% of the capacity is used, then we reach net zero energy. So quite an interesting story. In fact, we would get to negative energy consumption. We would be producing energy from this store, net production. So all in the end, doing more with less. And these are technologies that are available today. So there's really no reason not to do this. It's getting to higher energy efficiency, on-site generation and storage. And then basically, there are things that we can do even going further. So not only optimizing the energy bill, but we could also optimize in terms of carbon intensity and other things. We can play around with primary reserve capacity, providing fast frequency response to provide grid services, peak load shifting, and even seasonal buffering could be a potential here. So this is all helping to reduce carbon footprints and energy bills. And with that, back to you, Jonas.
Thank you very much, Hans. I think it was a very interesting insight to how we're working with supermarkets on a daily, from a holistic perspective. I like the idea about reduce, reuse, and create flexibility, and at the end also the opportunity to export. And I hope that the viewers and the listeners here enjoyed the behind the scenes sort of insight to what is possible today and what we can do, and also listening to how that there are these synergies between data centers and supermarkets, even though it's not quite obvious, but something that they can learn from each other here. And those are the discussions that we would like to take with you further. So I would encourage everyone listening in to reach out to either me or one of my colleagues. If not, then I hope you get a very nice rest of the conference. Thank you very much for participating.